Alright, so here we go with the second example for exponential growth. So bacteria in a lab grows in such a way that the instantaneous rate of change of bacteria is directly proportional to the number of bacteria present. So when we are looking at these problems, remember, we're looking at these words directly proportional. This means that we're going to use exponential growth. So on the test, on the AP test, in college, whenever you see this, we're talking about exponential growth. So first thing we need to do, write a differential equation that expresses the relationship. So in the problem, in the first part of the problem, there's no numbers, there's no variables, no anything. So what we need to do is just write a generic form of our differential. So this is just our, so dp, so population. You pick really any variable you want there. So over change in time equals kp. So that would be the answer for A. We just write a generic one with all of our variables. And then B would be to solve the differential equation like we did in the other video, or we just remember our equation. So the equation is going to be P equals C e to the kp, or kt, sorry. So that's part B. So as long as we remember our equation, so it's just this, an exponential format, so something we've been dealing with since Algebra 1. Alright, suppose that initially there are 5 million bacteria and 3 hours later the number has grown to 7 million. Write a particular equation that expresses the number of millions of bacteria as a function of hours. So we know if we plugged in 0 for time and 5 million to our P, that's what it ends up being after 0 hours. If we were to solve the equation, we would end up with the C value of 5. So we talked about that in the other video, that C is always the initial value. So when we're setting up our equation, we can say that C is 5. E to the K, we don't know what K is. We need to find K. And then 3 hours. At the end of 3 hours, we know that our equation would produce a 7. So that's what we're gonna write there. Now we know we have to use this equation to solve for K because we don't have any kind of rate of change. Like in the other example, we had rate of change. That's why we plugged it into this equation, our differential, to find the K value. So at this point, it's all algebra. We're plugging in values. We're plugging in known values to find unknowns. So now we can solve for this. So if we divide by 5, and then, well, just do it out. So divide by 5, we get e to the 3k. And then to get rid of e, we're going to natural log both sides, and then divide by 3. So we get natural log of 7/5, all divided by 3. That would equal k. So now we're going to plug back into our equation. We get P equals, we know our C is 5. E, now you can use this K value, you can write this out, this exact answer. So when we use it later, we're going to get a more accurate answer, or you can just use the decimal version, which I believe is 0.112 t. So this is our equation. That would be the answer for part C. Okay. Now we can use this to find other values. So we have a couple more things to do with this. So what will the bacteria population be 1 full day after the first measurement? So we can think of the first measurement as just the initial value. Other problems are going to be a little bit more clear what you're actually calculating. This one, we're just going to plug in 24 hours into our equation. So if we do that, again, 0.112, or the full natural log of the 7/5 divided by 3, and then multiply by 24. So we can run through this and calculate it, which I will do right now. This is 5e 2 times 24. We're going to get 73.511. Now remember, our equation outputs numbers in terms of millions, so this is in millions, so we have to write that out. Okay. And then F, when will the population reach 1 billion? So what we're doing here is we're plugging in 1,000 for P, because 1,000 millions is a billion. So we're going to plug that in. And then solve for time. So we would divide by 5, take the natural log of both sides, and then divide by 0.112. So we get natural log of 200 divided by 0.112. And this would give us, let's see, I think it's close to 2 days. Divide by 0.112. Yep, we get 47 hours. Let's see, 47.306 hours. Okay, so that completes the video. I will make another video about just solving differential equations in general, just so you can see that again. But that's it. Just let me know if you have any questions, and we'll go from there.